All right, hey everybody. I'm out at the FGNS. Yeah, the FGNS, which is actually the location of my club's observatories. This is, yeah, they've got the one up there. I think it's a 18-inch or something like that, and they've got a roll-off on this side. There's a whole bunch of telescopes in there. Some pretty neat stuff. If I get a chance, I'll go in and maybe get some pictures and show them here. I'm presenting here on exploding stars tonight, and we've got a public viewing with the club. A few clouds in the sky right now, but I think it's going to be a beautiful night later. And we also, I think we've got supposed to be a good night for the Perseids because tomorrow night's going to be cloudy. So anyway, stick with me, and I'm going to be presenting, and then we'll see if I can get some pictures at the end here for some of the equipment that we've got in our observatories. All right, my name is Doug. This is AstroAF.
So without further ado, let me introduce you and have you all welcome Douglas Reynolds. Hopefully these slides aren't too irritating and close some of these doors a little bit, but we don't want to get too big. Yeah, hello everybody. This is great. I'm so happy to see so many people turn out. So, and it looks like there's a lot of people here that aren't members, or at least that I don't recognize. So, anyway, welcome, and I really appreciate that you've taken the effort to drive out here. And for this exploding stars, I mean that's a draw, you know. So my favorite part of exploding stars are the nebula, the remnants that they leave behind, because I'm an amateur astrophotographer, and so I like to take pictures of these things, and I happen to be very photogenic, and I think I've been looking at the skies as long as I can remember, and when in the early 90s, the Hubble Space Telescope images started coming out mainstream for us, and I saw those, I was just absolutely blown away. And it was, I didn't know that, and maybe at the time you really couldn't, but to take photographs, and I photograph out of my backyard. And yeah, Carl mentioned I had a 70 millimeter refractor that I was using. I have since upgraded to an 8-inch Celestron Edge HD, which is a really nice telescope for imaging. And I just did that this May, and that has been a big challenge. It was my first Cassegrain style telescope, and had the 8-inch temperature came with an equally large learning curve. So anyway, it was a lot of fun. I'm finally feeling comfortable with it, and imaging sessions are going on. But so tonight we're going to talk about exploding stars, and which is the reason that we're here. But we also are here because this is a public viewing session. So after my presentation, which should take around 30 minutes or so, then I know we have at least one telescope out here in the parking lot from one of our members, and then we also have the observatory open over on this side. And if you go out this door and turn right, there's a sidewalk, and take another right, you'll come around the back of this building, and then there's a roll-off roof observatory that's right over here, and it'll have some red lights that illuminate. And if you happen to be able to see it, it says observatory on the side. So anyway, we welcome you to check out our facilities because we wanted to introduce that to you. I'm hoping that one of the reasons that you're here is you're interested in the Twin City Amateur Astronomy Club. And for me, I've been a member for a couple of years now, and it is an amazing group of people, and we really enjoy the community around it, the resources that are available, the learning, education, just camaraderie, picnics, and all kinds of neat stuff that we and our members put together. So we can have fun in this hobby, and that makes because the rest of the time I'm alone in the dark in my backyard. So and I think a lot of us spend a lot of that solitary time with our telescopes. If not with family, then on our own or with friends. So it's nice to have a community and share our experiences with and get answers to questions and things like that. So anyway, I invite you to reach out to any member tonight if you have questions about the club, if you have questions about astronomy. If someone doesn't know it, I'm sure that we can help try to point you in the right direction. So anyway, with that, I'm going to go ahead and get started, and we'll talk about the exploding stars. And this is the we're at the what is this? The FGNS, right? And this is the 2024 August 10th, 2024 TCAA public viewing session. Oh, by the way, you can also find the TCAA at tcaa.club on the internet. Oh, it's not. Yep. All right, let's see if I can figure it out. All right, so tonight I'm going to talk about the life cycle of stars, star formation. I'm going to talk about stellar nucleosynthesis, and I'm going to talk about supernova explosions, which is why we're here, right? And nebula remnants, which is my favorite part because they're beautiful. And so in exploring the life cycle of stars from creation, you can condensate in areas of vast molecular clouds. These are the nebulae. Ultimately, a star's self-destruction occurs in the final stages of its life, resulting from the conversion of hydrogen to helium, and finally to even heavier elements which cause atomic fusion become endothermic, which means that it requires more energy to fuse the heavy elements than is produced by the fusion. Eventually, the core can no longer support the weight of its own mass, and the inevitable collapse occurs. In some cases, the core can stand the collapse and produce a supernova. In other cases, the core is overwhelmed, being compressed into infinite singularity and forming a black hole. In the case of a supernova event, the resulting shock wave distributes materials across the interstellar medium, with newly formed neutron stars reaching a brightness exponentially greater in the night sky than even our brightest star Sirius. The newly formed supernova remnants then have the potential to become a new star-forming region where the cycle of creation gets even. So star. Let me grab. So star birth occurs in vast piles of aggregated molecular matter, which exists in galactic disks. And in these regions of matter, there are smaller areas of condensating matter. And the condensating areas of the matter can be caused by random fluctuations in the surrounding molecular cloud or external factors, such as shock waves from supernova or collisions of galaxies. As the condensating matter flows inward, a protostar begins to form, and it develops in the central core the surrounding gas and dust. This is supported by the developing pressure of the clouds. Within this period of star formation, there is a constant inward flow of gas and dust surrounding the protostar in the form of an accretion disk, whose inward flow increases the central density and temperature as a result of the increasing compression of the inflowing matter at the core formation area of the protostar. So eventually a tipping point is reached, and this occurs when the pressures and temperatures reach a level where nuclear fusion of the matter is ignited. So we have low and high mass stars, and I think that's kind of in comparison to our sun, which is, sort of everything else that as we talk about it is sort of judged upon the size and mass of our sun. So when I'm speaking here further on this and making comparisons, it's all kind of relative to our sun, our solar mass, and our solar brightness and things like that. So low mass stars are defined as having 8 or less solar masses. So I guess that means that our sun is a low mass star. It's thought that understanding of low mass star formation is pretty well understood, but high mass star formation is much less understood. So, and the reason it's not understood as well is because we believe that the emissions of a massive star would be great enough to basically blow off the accretion disk that surrounds it, that's feeding it the material that allows it to continue to grow. So there's a couple of models, theories around this. One of them is that the accretion disk forms a jet around and through, creates a tunnel into the like a cavity, into the star that's forming, and this allows a directed flow of radiation out through that cavity. That's kind of like a release valve, and that directed flow won't blow the accretion disk away all the way around the star. So, and then there's another theory on this model that the merging of 2 or more low mass stars, or from a combination of a low mass and a high mass star with the same gravitational potential, may accrete from the same molecular cloud. In that way, massive star. So this is kind of a neat topic, which is stellar nucleosynthesis. And so this is the nuclear fusion process which occurs within the stars where new elements are created. And it's a really important aspect of the star's life cycle that leads it, from its star formation into its later stages of the star's life. So the initial mass distribution of the star is calculated against the galactic mass, and it's known as the initial mass function. In order for a star to sustain fusion, it must have a solar mass of at least 8%. So stars with smaller mass, less than 8%, they do not have enough gravitational binding force to create the pressure that's needed to generate temperatures high enough in order to ignite nuclear fusion. So stars of this type, which are not technically stars, are known as brown dwarfs. So stars that are formed with greater than 8%, but still less than 40% of solar mass, are able to ignite nuclear fusion. Yet due to their lower mass and temperatures, they emit less energy than our sun. They have fainter emissions and fewer temperatures. So red dwarfs fall into this category. Red dwarfs give off more of a light in the red wavelengths and are designated. And they have fainter emissions and they're cooler. They have cooler temperatures. They fall. The red dwarfs fall into this classification of stars, as I mentioned, and they comprise upwards of 78% of the 200 billion stars in our galaxy. So stars are designated by type and defined by attributes such as their temperature and color. Stars falling on a main distribution plot, including our sun, are known as main sequence stars. These distributions are shown on our Hertzsprung-Russell diagram, which I'll show you next. We just have to look at what that diagram tells us. The main sequence stars have classes which include types that are classified by what's called the Morgan-Keenan system. And this is a system of classification of stars from hottest to coolest. And the MK system defines type O, B, A, F, G, K, and M stars. And these are specifications of the spectral and related temperature characteristics of different stars. So, for example, our sun is a type G, yellow star, with a surface temperature of around 5,800 Kelvin, which is 5,526 degrees centigrade. And so in this next figure, we'll show how it illustrates how the sun is positioned on the main sequence in relationship with other types of stars. So this is the Hertzsprung-Russell diagram. And on it, we've got a couple of axes. So on the y-axis, we have illumination, so the brightness of the star. And on the x-axis, we've got temperature of the star. And if we take coordinates, which is basically 0, and then the temperature of our sun, we can see our position of the sun on the main sequence. Which is there. So this distribution plot right here is all of the stars that are kind of similar to our sun, and their characteristics are very common in the galaxy, and probably throughout other galaxies as well, as far as we know. But in terms of our own galaxy, these distributions of stars here along these lines are the most common types of stars that we have. Now, as stars move through their life cycle, they begin to diverge from the main sequence. And so, if you see up here, the red giants here, they have cooled down, but they've gotten brighter. So they've moved up off of the main sequence, up in the upper right corner. Conversely, white dwarf stars are hotter, but not as bright. So they diverge down to the lower left. Okay? So basically, what this is telling us is how these stars relate to one another in their brightness and temperature, and then the distribution, and the percentages of stars that we have, that fall on the main sequence, which is the predominant number of stars that we have in our galaxy. If we look at the other diagram that I was talking about, so this is the stellar classification of the main sequence. So as I said, I think the easiest thing to do is think of it in terms of our sun here. And so our sun is a classification G star. So we're looking this line right here. And so it defines stars that fall into a temperature range of 4,900 to 5,700 degrees Celsius. And they generally have weak levels of hydrogen. Since our sun is what everything is being compared to, our sun is a sequence of the solar mass of 1. Okay? So here, any stars that range between 0.9 and 1.1 fall into this G category. Okay? And then stars of G type, like our sun, make up 7.6% of the stars in the main sequence. So you can take a look at like the other star types, their various temperatures, how many they make up, as far as where they fall in the main sequence and how many of those stars exist in our galaxy on the main sequence that fall in those categories. So fusion reactions. A star has two key zones related to fusion. It's got a hydrogen envelope around the outside, and it has a hydrogen burning zone in the interior, which is the core. So the core is the location in which nuclear fusion occurs. Fusion is the result of two nuclei merging to become one atom. So a hydrogen fusion reaction within stars fuses two hydrogen atoms together, producing a helium atom. The hydrogen atoms consist of two isotopes, one with deuterium and one with tritium. This reaction produces an isotope of a lesser mass than the sum of those that fuse together. Tritium has one proton. Well, we can explore this in a let me go into it a little bit further. So the isotopes, protons, and neutrons end up being less in the result of the fusion than what the sum of the neutrons were in the two atoms that fused together. So the resulting helium has two protons and two neutrons. But we had two protons, we had two neutrons, and for each of the other isotopes. So we ended up losing a neutron off, and that is called a mass deficit. And so this is like the key important factor of how this occurs, because in order to make up for that mass deficit, energy needs to be created. And that's the energy that is this fusion of the star's core. And the conversion of mass to energy and the amount of energy created from the reaction is enormous in comparison to the energy that was required to fuse the atoms in the first place. So it's an energy surplus over the top of how much energy it takes to have that fusion reaction take place, which is we're really interested as a society in trying to develop fusion energy. This is why, because if we can create more energy than it took to make it, then that's going to increase our technological abilities all across humanity. So, stellar nucleosynthesis continuing, the evolution of an exploding star. The stellar evolution is the process by which a star evolves over time. From its creation as a protostar to its eventual demise, which can result in several different outcomes. As mentioned earlier, stars are formed in galactic pursuits of vast molecular clouds. And a star's life cycle is directly dependent upon its mass, with truly massive stars having much shorter lifespans, in the order of millions of years, than that of a typical main sequence star. Low-mass stars can have lifespans of trillions of years. The main factor which determines a star's lifespan is the rate at which a star fuses hydrogen and helium. A star reaches a state of equilibrium, which is known as hydrostatic equilibrium. So this is where the fusion core generates enough outward force energy to support the inward force of the star's matter. So this is that equilibrium. The star is always trying to maintain this equilibrium through the energy that the core creates, and then the mass that surrounds it in the envelope that's pushing down the planet. If it didn't have that equilibrium, it would be a very short-lived star. And we might see that like in a star like Betelgeuse would be a good example of where it's kind of lost its equilibrium, it's grown into a red giant. It is an interesting star because it moves and it's been contracting and expanding. We don't know exactly what it's going to do. It's not typical, but it's a very interesting star to keep your eye on for what might happen to that, and potentially in our lifetime. So we could be lucky enough to actually witness that type of event. But anyway, So a star reaches a state of that equilibrium, and again, that's known as hydrostatic equilibrium. And that's where the fusion core generates enough outward force energy to support the inward force of the star. Okay? This prevents further collapse of the material into the core. As the star ages, it continues to fuse hydrogen into helium. An abundance of helium ash is deposited into the star's core. So the amount of helium ash continues to grow for the entire life of the star, while the hydrogen fuel for fusion is slowly spent. Helium is denser than hydrogen, and the helium core contracts, creating even more heat. And the essential temperatures and pressures build to a point where the energy output of the core overwhelms the outer hydrogen layers, mass, and gravity. In the case of a red giant star, it can push them out to sizes that can reach the equivalent of Jupiter's orbit around the sun. So truly massive. So we'll look at a diagram here. Might be an oversimplification. However, this is a hydrogen envelope that surrounds the hydrogen burning core. And as the nuclear fusion occurs and creates helium, the helium ash builds up into this core. And as the core becomes denser and more compact, it gets smaller while gaining more energy and pushing the envelope outward. So this is the end game of the star's life. And as the result of the central temperature and pressures becoming extreme enough that helium can fuse into carbon. This increases the energy output of the core dramatically, and the loss of the hydrostatic equilibrium, which is crucial for the star maintaining its overall balance of its pressures and gravity. So, pushing the unfused hydrogen outward is the result when this happens, because the energy at the core has grown so great with the density of the helium and the temperatures that are being created that it overwhelms the outer envelope. So it's at this point that the core will produce enough pressure and heat to begin fusing this carbon into iron and even heavier elements. And so this is really the death note for the star when it gets to this, because at that point, which the star's demise is inevitable, because the fusion reaction then becomes what's called endothermic. And endothermic means it's taking more energy to fuse than it generates from the fusion itself. So the core is now burning more fuel to make the fusion than the energy output that it has, which means that it can no longer support the outer envelope because the imbalance, it doesn't have the equilibrium anymore. So the endothermic reaction consumes the energy of the star, and eventually it's not enough energy generated to support the weight of the star's mass, and it falls in upon itself and floating. So as the star core changes due to the mass and temperature, it continues to seek equilibrium and dramatically affects the star's size and color. So when the star is no longer able to maintain equilibrium, a collapse occurs, the result of which depends on how massive the star is. So there's two potential outcomes when the equilibrium is lost and the star collapses. So the first is a neutron star is formed when the mass of the star is not enough to fully collapse the star core. And in this case, the collapse results in a supernova with the hot core remaining surrounded by the formation of a nebula that's created from the explosion of the star's outer layers. And that outer layer matter remains in a nebulous form, expanding. So there's a tremendous shock wave that occurs as a result of this that propagates out from the star, carrying all this remaining matter with it. For the truly massive stars, the result is more of a whimper, and where the collapse results in the core crushing into an infinitely dense singularity and the formation of a black hole. Now, in some cases, there's still nebulosity that is created following the implosion that becomes a black hole, and this will become an accretion disk forming around the black hole seen through its event horizon. So supernova types, we have a couple main types of supernova. We have the type 1A supernova. So this type of supernova results from a binary star system where a white dwarf is accreting matter from its binary companion. And as the white dwarf's mass increases from accreting from its companion star, the core reaches a critical density at some point when it has gathered enough material from its companion. And this critical density can result in an uncontrolled fusion of carbon and oxygen. And this uncontrolled reaction results in the star's detonation, resulting in a supernova. So this is our exploding star. In a type 2 supernova, the supernova mark the end of a truly massive star life. So the star has exhausted its fuel and its energy and can no longer support the weight of its own mass. And when the star iron core is massive enough, it will deflect the imploding matter and exploding into a supernova. So the core in this case is not massive enough, or the forces that coming into it were not great enough to actually condense that core further, press it into singularity. So it was strong enough to withhold the forces coming in. It bounced off the core and exploded and created the supernova. So a supernova explosion. When a star explodes into a supernova, there is an explosive release of energy of approximately 10 to the 26th power megatons of energy. This forms a shock wave which propels the star's outer matter into the interstellar space to become a supernova remnant. The explosive release of energy during a supernova produces an incredible brightness, outshining even the brightest stars in the night sky. Supernovae are so bright, in fact, that the absolute magnitude can reach -19. This means a supernova that's approximately 32 light years away from Earth would be 1.5 times 10 to the 7th times brighter than Sirius. And Sirius is the brightest star in the night sky with an apparent magnitude of -44. So it's truly amazing. So the shock waves are created which ripple through this interstellar medium, and as I mentioned in starbirth, these shock waves can disrupt molecular clouds, causing areas of density that can then begin the process of new star formation. A supernova shock wave can cause compression and resulting heating of the interstellar materials up to 1 million degrees or more. And this is truly the full circle of star creation and life, death, rebirth, and without this process, it's believed that there would be no new stars formed. So supernova remnants, nebula remnants. This is my favorite. This is what I love about it. And so I love the explosion part, but I love the system. Because we get to see this a lot, because it's happened a lot, and these nebula remnants stick around for a long time. You know, the supernova, when they occur, we don't know when they're going to happen, and they actually, from their peak brightness, it can only take a couple weeks before they fade back down. So it doesn't necessarily take a long time for a supernova to sort of fizzle out. And I was lucky enough to actually get a picture of a supernova last year. It's probably, maybe that's a once in a lifetime thing. You know, maybe. So anyway, supernova remnants, SNRs, are simply the remains of a star that has been distributed across interstellar space following a supernova. And these remnants are most often observed as nebula and are generally made up of hot glowing ionized gas and particles. These remnants can also contain materials that were caught in the supernova shock wave and brought along for the ride with the rest of the materials. The shock wave itself often forms the outer boundaries of the SNRs. The expansion of the shock wave and the surrounding space interacts with interstellar medium, creating a beautiful complex structure. Supernovae are responsible for the creation and dispersal of heavy elements such as iron, gold, and uranium. Supernovae are also responsible for creating lighter elements such as hydrogen, helium, carbon, and oxygen, as well as amino acids in the water, which really are created from stardust. Supernovae play a significant role in the formation of new stars, planets, and the building blocks of life. SNR are generally classified by their shape, form and structures resulting from the supernova shock wave that distribute the star matter and swept up interstellar materials. There are three main classifications of SNR. We have the shell type. These are large distribution of heated materials. The type often has a ring-like structure. Due to our perspective, we observe more heated gases and debris along the edges of shell type than in the center. This gives it the term limb brightening. This describes the brightness of the outer edges as compared to the middle of the SNR structure. We have a crab type of nebula, and these are also known as pulsar wind nebulae or clarions. And crab type remnants are more blob shaped, and as compared to shell type remnants. And the crab nebula is a well-known, probably the most famous of the crab type nebula, and the reason that we call them crab type is because of the crab nebula. So it's the namesake of that type. And we have a composite type, which basically resembles characteristics of both shell and crab types. So, depending upon how they are being observed in the electromagnetic spectrum, they may have characteristics of one, the other, or both types. There are two types of composite remnants. There's a thermal type, which appears as shell type in the radio spectrum. In X-ray, they appear as a crab type. The thermal composite remnant spectra have spectral lines indicating hot gas. True shell type SNR don't show these spectral lines. Clarionic appear as crab type in both radio and X-ray, but also have shells. Clarionic type X-ray spectra do not show spectral lines in the center, but they show it around the outside. So basically, these classifications are based on our observations through different types of telescopes, radio telescopes, X-ray telescopes, visual light telescopes. So they all create different ways that we give these classifications, and it's generally based on those characteristics. So supernovae are one of the most important natural events occurring in our universe, and they're critical to the formation of new stars and celestial objects, including planets. And supernovae create the molecular clouds of gas and matter, which become the birthing areas for these newly formed stars and objects. So each star, though unique, goes through a life cycle with much similarity to other stars. However, depending upon a star's mass, the lifespan of massive stars can be trillions of years less than that of the lowest mass stars. In the context of exploding stars, we're interested in the more massive stars, exceeding 8 solar masses, whose mass overwhelms the force ability to maintain hydrostatic equilibrium. It is not enough to fully collapse the core into a singularity, forming a black hole. Thus, a neutron star is instead created when the star's hydrogen shell is blown off with an unimaginable force, extending out into the interstellar medium with a double brightness. The resulting celestial structures, known as nebulae, are areas of hot gas, dust, and a variety of elements which set the stage for the next cycle of creation. So I want to thank you very much for attending tonight, and it's really my pleasure to have the opportunity to do this. Like I said, I spend most of my time alone in my backyard, and this is a very comfortable thing. And I like pushing myself, and I hope that you enjoyed this presentation. You know, as I said, I became infatuated with this deep sky and passionate about it. And, you know, I hope that you take the opportunity to go out and go around right here and follow the sidewalk and go through these telescopes. It's truly amazing. And, you know, and I hope that in that process you can spark or something that ignites that passion in you that lets you also experience this amazing and interesting, unknown and beautiful universe. Thank you.